Welcome to part 3 of our How to Design and Build an Airplane series. In this video, we're going to be doing the aerodynamic design of our main wing. As I've mentioned previously, there's a lot of information in aircraft design, and I've read almost none of it. I've Googled a few things and primarily used Aircraft Design, a Conceptual Approach by Raymer as my guide for this project. It's a pretty solid book if you're interested in the subject. The information can be found below. Analysis without numbers is just your opinion. So in this video, we're going to be getting into doing actual calculations. For all the calculations I did in this series, I used an Excel spreadsheet to make life easier for myself. Anytime I'd find an error in my calculations or in my formulas, I could just go back, change the cells, and we get the right number automatically. It also helps eliminate arithmetic error with multiplication and subtraction, things like that, ultimately just making design iterations a lot easier. Step 1 of the aerodynamic design is going to be to select the operating speed of our aircraft. This is one of those spots where our constraints are really going to help us out. If you remember back to video 1, one of our constraints was that we had to fly relatively slowly. So I selected 55 feet per second as my maximum operational speed. And that's 37.5 miles an hour, or thereabouts at least. Now, I know this seems kind of fast, but we're still at only 5% the speed of sound. Now, just like one of my favorite movie characters, Mark Watney, pointed out, engineers don't really use the term fast, or at least in a universal context. In the context of a project or building an airplane, fast is considered usually to be the speed of sound. But hey, what do I know? I'm just the man from the internet. Now that we know how fast we're going to be flying, we need to determine the other dimensions of our wing. There's 3 things that characterize your wing: the aspect ratio, the span, and the chord. We've already chosen our aspect ratio at 7, and we know that our wingspan is going to be 36 inches. So we're going to use the equation aspect ratio is equal to span over chord. We're going to multiply both sides of this equation by chord over aspect ratio. A few things cancel out, and we find that span divided by the aspect ratio is equal to our chord. So we divide our span of 36 inches by our aspect ratio of 7, and we get that our chord is 5.125 inches. We round it up because this way now we have a nice even 5 1/8 inches, because I don't know about your ruler, but mine only measures in eighths and sixteenths, not tenths. So now that we have that, we need to pick an airfoil. There's literally thousands out there that you can choose. I used airfoiltools.com for all of my information. They provided all the technical data that I need, from coefficients of lift and drag to plot points so you can accurately make each shape. I could probably have about a 25-minute video on how airfoils work and the various shapes and why you would choose each one. But I'm going to leave a lot of that research up to you because this is your project after all. A common approach in the aero design competition was to look at the ratio of the coefficient of lift to the coefficient of drag. You obviously wanted to maximize your coefficient of lift while reducing your drag as much as possible. There are shapes that allow you to do this, and it leads you down a different path than the one that I chose. I chose to pick an airfoil that had the maximum amount of lift possible. This will allow me to fly a little bit slower while still being able to have a decent amount of payload if needed. So I chose the Douglas LA203A airfoil for my main wing. This airfoil has a high lift coefficient, but I do pay a penalty in that it also has a relatively high drag coefficient. I know what you're thinking. We haven't provided any numbers to make this more than just my opinion. In order to provide those numbers, we have to select an angle of attack for our airfoil. If you draw a line from the leading edge to the trailing edge of your airfoil, this is the chord line, and the angle between that and your horizontal is your angle of attack, which is represented by alpha. So on Airfoil Tools, you look at all of these plots that they provide with things like coefficient of lift versus alpha, coefficient of drag versus alpha, ratio of lift to drag versus alpha, and a few other plots. So when you're looking at these in the first place, you're going to see about 6 different lines for different Reynolds numbers. And the Reynolds number is a non-dimensional number that characterizes the flow. It tells you basically whether or not the flow is laminar or turbulent or somewhere in between. It's a common calculation in fluid mechanics, and it's a really easy one to do, but they have a Reynolds number calculator on this website, so I recommend using theirs just to make it easier on yourself. All you have to provide is your airspeed and your chord length. So with our airspeed of 55 feet per second, and our chord length of 5.125 inches, we end up with a Reynolds number of about 150,000. Now there's no 150,000 line in this, but we are going to go back and use the 200,000 Reynolds number, only because I think that at 150 we'll be closer to the 200,000 line than the 100,000 line. I know we're in the middle, but as the flow goes along, it's going to become more developed and tend to act like the higher Reynolds number in this case. Now the proper thing to do would be to interpolate using all of the available points, but that's a lesson for another time. Okay, so back to the selection of alpha. So I chose my alpha to be 5 degrees because if you look at these plots, the coefficient of lift peaks out at around 10 degrees angle of incidence. Now I chose 5 because if we have any changes in wind direction or any turbulence in the air around the airplane, we could suddenly lose lift and cause the airplane to fall and become uncontrollable. I feel like 5 probably gives us a little safe cushion either way, where we don't lose lift if we artificially increase or decrease the angle of attack. So now that we've selected our angle of attack, we're going to go into these charts over here and go to 5 degrees angle of attack and pull out our CL, CD, and CM. Now we're going to calculate lift at our maximum velocity using the lift equation, which is L is equal to coefficient of lift times 1/2 rho v squared times the surface area of the wing. CL is our lift coefficient that we pulled from Airfoil tools. Rho is the density of air. And v is our fluid velocity, or 55 feet per second. And SW, our surface area of our wing, is the top-down surface area, so it's going to be your chord times your span. So this 1/2 rho v squared in the middle of our equation is basically an energy. Energy can be represented by the letter Q, and we're going to pull that out of our equation and put it off to the side because it's going to be the same for all of our lift, drag, and moment calculations. Now we're going to calculate a value for Q. We're going to do 1/2 times 0.00238 slugs per cubic foot times 55 feet per second squared. And we get that Q is equal to 3.6 slugs per cubic foot. Slugs are an actual unit. They are the imperial system for mass. Pounds are used for force, and usually we weigh ourselves in pounds, whereas in the metric system they weigh themselves in kilograms, which is a mass and not a weight. I know it's really weird, but basically you just have to make sure that all of your units match up and that you're multiplying slugs by slugs, feet by feet, and seconds by seconds, because there are instances where you're going to have different units and you need to make sure that you're multiplying the right units together to get the right answer. Now we're going to calculate lift. We're going to multiply our coefficient of lift of 1.2249 times our Q of 3.6 times 184.5 inches squared. That we need to convert to feet, so we're going to divide by 144 inches per square foot. And we find that when we multiply everything together, we get 5.65 slug feet per second squared. That's not pounds. We have a problem, right? No, that's actually what we do want, because slug feet per second squared is actually pounds. Go ahead and Google it. I'll wait right here. Okay, now we're going to move on to calculating drag. And the drag equation is a little different than the lift equation, and I'm going to blow your mind right here. I know, so much different, right? So we do have one little complication with this, in that our coefficient of drag that's listed here isn't just the coefficient of drag that we pulled from Airfoil tools. It's that plus an additional coefficient of drag that's based on the coefficient of lift, called induced drag. Now the coefficient of induced lift is equal to the coefficient of lift squared divided by the aspect ratio times pi times an efficiency factor E. We've seen all of these numbers before, with the exception of this efficiency factor. Now for a boxed wing, E should be 0.7. If you're using an elliptical wing, this number will be 1 because you'll have fewer tip losses, like I mentioned, because the elliptical wing is more efficient. So we multiply 1.2249 squared divided by 7 times pi times 0.7, and we get that our induced coefficient of drag is 0.0971. So now our drag force is equal to the sum of 0.0971 plus our drag coefficient that we pulled from our plots, 0.0190. That's multiplied by 3.6, and then multiplied by our surface area of 184.5, once again dividing by 144 to convert to feet. And that gives us a drag force of 0.5356 pounds at 55 feet per second. The last thing we're going to calculate is the pitching moment for our main wing. If you don't know what a moment is, it's a torque or a twisting force. This force is due to the uneven pressure field around the wing that will cause it to pitch up or down naturally. This force is countered by either the use of a tail, like we'll be using, or by adding wind sweep. When calculating the pitching moment, it's important to note the sign of your coefficient of pitching moment. A positive coefficient means that the wing will want to pitch up, and negative means it will want to pitch down. We're going to calculate the pitching moment using the equation pitching moment is equal to Cm times Q times surface area of our wing times the chord. So plugging in our numbers, we have our pitching moment, which is minus 0.1546 times 3.6 times our 184.5 divided by 144 for square feet. And we're going to multiply that by our chord length of 5.125 inches. We get that our final pitching moment is negative 0.3045 foot-pounds. The negative sign indicates that the leading edge of our wing is going to want to move down. Okay, that's it for the aerodynamic design of our main wing. Thank you for watching part 3 of our How to Design and Build an Airplane series. Click for part 4, where we're going to do the aerodynamic design of the tail. If you have any comments, questions, concerns, ideas for future airplane or non-airplane projects, leave them in the comments below. Please like, share, and subscribe. Thank you for watching.